Hi. In this short video, I wanted to address a question raised by one of my viewers regarding the forward current flowing through a diode when the applied voltage is extremely small, for example, in the millivolt range. And his question was whether there would be a measurable current, and if so, can we do some experiment to show that? And the short answer is yes. The current flowing through any diode is a continuous function with respect to the voltage applied, whether it's forward biasing or reverse biasing. And we're all familiar with a typical diode's IV curve, which I will show here. So for your typical diode, the IV curve can be drawn like something like this. Basically, in forward region, we would observe a sudden current rise after the voltage. So here is our voltage, here is our current. After your voltage exceeds certain level, let's say a VF, that's your forward voltage drop. And in the reverse region, again, you won't see any significant current till you reach a point where the voltage is the breakdown voltage. So here's a VB. That is the curve we are all familiar with. So now the question is, actually, what happens in this region when the voltage is extremely small? Can we measure anything? So that's the question asked by the viewer, and which we will demonstrate in this video. And for that, we have to resort to the diode equation. We know that the IV curve for an ideal diode can be expressed via the Shockley diode equation. By the way, not to be confused with the Schottky barrier diode. The Schottky barrier diode, which is a metal semiconductor junction instead of a semiconductor junction diode. And the main characteristics of a Schottky diode is the greatly reduced forward voltage drop, typically at around 0.2 volts. These names are pretty close, unfortunately, but they're not really related. Perhaps even more confusing is that there actually is a type of diode called the Shockley diode. Instead of a single PN junction, the Shockley diodes are PN-PN devices. Anyway, so today we're actually talking about the Schottky diode equation. Okay, so let's get that straightened out first. So anyway, the ideal diode, the forward current or the reverse current, can be expressed in the equation something like Is times e to the alpha Vd minus 1, where the alpha is a constant, Is is the reverse bias saturation current, which is a constant. So let's take a little deeper look at the alpha. Alpha can also be expressed as 1 over n Vt, where the Vt, again, the n is a constant, which I'll just ignore here, but the Vt is it's called a thermal voltage, which we can further express it as Vt equals Kt over Q. So here we have a couple more constants. The T is the temperature in kelvins, and K is our Boltzmann constant. So for those who don't know, it's just a constant, but the value K is 1.38 times 10 to the minus 23 joule per Kelvin. And Q is our standard charge of an electron, which is 1.602 times 10 to the minus 19 coulomb. Okay? So again, the Vt is a constant, and in room temperature is typically somewhere around 26. So Vt roughly is 26 under room temperature, which is around 300 kelvins. Let's rewrite this out in a cleaner fashion. So basically, I equals Is over E to the Vd over nVt, which is your alpha, minus 1. And as we can see, the Vt, as we mentioned earlier, in room temperature is around 300. So this term is 30. So this term is extremely small. Using Taylor expansion, we can express that term as 1 plus Vp over nVt, and then we'll have the minus 1. So the current essentially becomes I equal to some kind of constants. Okay, so we call it beta times Vd. So as we can see, when the forward voltage is very small, we would expect that the curve is something like a straight line. So this is really counterintuitive. That's why I wanted to do some experiments to see if we indeed get what we have in this theoretical equation. So because of the forward current would be extremely small, given the low forward voltage, we want to use our Keithley 614 electrometer to measure the current. And for the voltage we're going to apply, we're going to use our Chromite MV216A voltage standard. We set it right now, you can see that in millivolt mode. So what I'm going to do is I'm going to cycle the voltage from 0 all the way up to a couple of millivolts in the increment of 0.1 millivolt. So let me set it up and we will take a look at the experiment. And here is our experiment set up. By the way, the reason I need to put the whole thing on a piece of plywood is because this surface is a dissipative surface, and it in fact has a resistance in the giga-ohm range. So that resistance itself would affect the measurement and the current flow of this sensitive measurement. So ideally I should put the whole thing on a stand and with extremely high resistance, but I think a piece of plywood should be sufficient for this experiment. So let me briefly describe the setup. Here from the left you can see the leads coming in is from the voltage standard, and the positive is hooked up to this positive of the diode, and the negative goes through the positive input into the electrometer to measure the current. And the electrometer's terminal comes back here. This is the negative, and I connect it directly to the voltage standard, so forms the closest circuit. And because of the current is so minute, the noise is very high. So in order to reduce the noise in the measurement, I came up with this kind of a poor man's shielding device, and you can see that the inside is actually lined up with the tape, so that it won't be able, it doesn't short out the components inside. But this Faraday cage essentially is grounded through the triaxial cable, so that helps to reduce noise. Anyway, so even like this, the noise is actually still pretty noticeable, and even if I just move around, and as I showed earlier in some of my videos in the measuring current using electrometer, and you will see that even just moving slightly around sometimes affects the measurement. But nevertheless, when I put this whole thing in, the current is actually pretty stable. Unfortunately, during the setup, I cannot have both the electrometer and the voltage standard in the picture at the same time, so I'm gonna just show you the electrometer, and I will read out what I'm dialing in for the voltage setting, and we'll observe what is the readout on the electrometer. As you can see here, I set the electrometer into its most sensitive current range mode, and right now we're in the current range, so we read the uppermost line, and right now it is set to reading picoamp, and the range is 20. So right now we're reading from 0 to 20 picoamp. And as you can see, even with the shielding we put in, because of the other side of the cable from the voltage standard is actually not shielded. So even if I'm just waving my arm here, you can still see that the current jumps quite a bit. So we just have to wait till it settles for each of the readings. Now I'm going to walk to the other side of the table and adjust the voltage standard to see, and then we'll get a reading for each voltage point we're at. So I'm going to read out the voltage I'm setting, and we will do the current measurement here. Okay, so now let it settle again. So I'm going to change the voltage to 0.1 millivolt. And as you can see, I put it to 0.1, it immediately jumped to somewhere in a range of 3. So let's call it 3, because right now, when the resolution is high, it really jumps quite a bit. And as we increase the forward voltage, we will see that the current will stabilize a little bit, because we will later on switch to a higher range, and we will have less of the variation in the readings. But anyway, so let's now move to 0.2 millivolts. And it's settled somewhere around 5.7. So let's call it 5.7. And 0.3. .3 and 0.4 millivolts. I have 11. Let's call it 11. 0.5. 13.6. 0.6 millivolts. 1626. So that's a picoamp. So right now we're there's a 16.26 picoamp flowing through the diode, and I'm going to try to see if we can switch it to the next 2.7, because that is actually reaching the limit of this range. But let's see. So right now it's 0.7 millivolts, and we are joined about 18.9. Let's just say 18.9 picoamp. So now I need to switch the range to the next highest, because I'm going to switch the range to 200 picoamp. Okay, so now I'm going to keep stepping up the voltage, and we will keep the reading going on. It's now 0.8, 21.5, 0.9, 24.2, and I'm going to change my voltage standard to 1 millivolt. So I'm going to change this back, and 1 millivolt, 26.8, 1.1, 29.4, 1.2, 32.1, 1.3, 34.7, 1.4, 37.3, 1.5, 40.1, 1.6, 42.7, 1.7, 45.4, 1.8, 48.1, 1.9, 50.7, and 2 volts, 53.5. So what I'm going to do is I'm going to plot what I just got. I just written down these the voltage measurements we have when we sweep from the input between 0 volt and 2 millivolts in a step of 0.1 millivolt, and we're measuring the output current in terms of picoamps. So right now the measurement is done, and I'm going to plot this to see what the kind of relationship we got. And here is a list of data that we gathered as we measured from 0.1 millivolts all the way up to 2 millivolts in a 0.1 millivolt stepping. We measured the forward current ranging from somewhere between 3 picoamp all the way up to 53.5 picoamp. So to draw that relationship in a spreadsheet, and here's the result we get. As you can see, that is exactly a straight line as we predicted earlier, because we are in a pretty linear region of this diode. And so as it goes on, as the voltage further increases, and we're going to see more of a exponential property of that line. And so the diode I used here is a 1N4004, which is a standard rectifier diode. And the reason I didn't use a signal diode like a 1N4148, for example, like this one, is because this is has a glass casing. And typically the glass casing doesn't really matter, but in this case actually it does matter, because the glass casing can allow light coming through, and the minute photovoltaic effect actually can be measured, so it will skew the result. So I'll show you briefly here. So right now I'm going to remove this and put the signal diode, which is a glass case here. So, and the actual reading will be slightly different because of different diode characteristics. But let me changing the forward biasing current to the voltage to roughly let's say 10 millivolts. Okay. So now what I'm going to do is I'm going to shine some light on the diode, and we want you to observe the current measured. So right now we're drawing about 40 point somewhere in the 40. That's the forward current right now. So now I'm going to use my flashlight here. I'm going to shine directly onto the diode. And as you can see, it dropped significantly. Right now it's back to 26, 23. And if I remove the light source, it goes up to 39. So clearly this would have made the results more difficult to characterize. So that's why I used a plastic case diode to begin with. So now we have both experimentally and theoretically shown that for a diode that is forwardly biased, with a very small forward bias voltage, the current going through the diode is approximating a straight line. So I hope you learned something new, and hope you enjoyed the video. If you did enjoy the video, please give it a big thumbs up, and let me know what other topics you want me to cover in the comments, and I will try to accommodate those. And as always, please share and subscribe, and I will catch up with you next time.